Hello and welcome to today's webinar about an efficient and comprehensive CFD solution for positive displacement pump modeling in Simerics MP+. Let's begin by looking at the general working principles of positive displacement pumps. These principles also apply to other types of PD machines, such as PD motors and PD compressors. Here is an animation of a gerotor pump in action. As the rotors rotate, we can see that the cavities between them are constantly changing in size and shape. Expanding cavities form a suction site as liquid is pulled in, while contracting cavities form a discharge side, pushing liquid out. These cavities have highly irregular shapes that are continuously moving and deforming. The continuous relative movement between the solid parts necessitates clearance in the form of tiny gaps in the design, small enough to separate the high pressure and low pressure regions. The pressure differences in positive displacement machines can range from several bar to several thousand bar. Additionally, as these machines typically operate at high speeds, cavitation is a common occurrence. Now let's take a look at the technical challenges faced in the simulation of positive displacement machines. The first challenge is creating and controlling a mesh that can incorporate the movement and deformation of the fluid volume or volumes. Shown on the right are two typical PD machines. The top image shows a variable displacement external gear pump, and the bottom image shows a twin-screw compressor. The complex and distorted cavities present in both models make creating a suitable mesh incredibly difficult. There are also typically micron-level gaps that can make meshing more difficult. Most general-purpose moving mesh methods are unsuitable for positive displacement machine simulation. An extremely fine mesh is required to fill these gaps and can lead to an inefficient mesh with a massive cell count. The number of time steps must also be limited in order to map simulation results from one mesh to the next. Even after creating an adequate mesh, robust and accurate cavitation models must also be implemented to capture important cavitation erosion phenomena. Modeling of extremely high pressure gradients and flows through small gaps are always a pain point in CFD simulations. Even after all of the above points have been addressed, the last major challenge, especially for commercial codes, is creating a workflow and interface that makes simulation setup practical and easy to integrate into an end user's design workflow. So then how does Simerics MP+ address all of these issues? Let's start with its advantages in meshing. The general consensus in the simulation community is that the only practical meshing solution for PD machine simulation is a customized moving deforming mesh designed specifically for each PD machine type. Most of these meshes utilize very complex mathematical and numerical algorithms. This approach is difficult and often impossible in most cases for end users to implement. However, Simerics MP+ has built-in mesh templates for most of the PD designs in use today. Each template in Simerics MP+ contains a guided workflow that allows any user to quickly and easily create a suitable mesh for their application, like the one shown on the right of a gerotor pump. Another advantage of Simerics MP+ is its advanced cavitation model. This model is based on the well-established Rayleigh-Plesset equations, which were derived from vapor bubble dynamics. Simerics further expands the original model to include free and dissolved non-condensable gases, such as air. Compressibility of liquids and gases are all taken into account, and mixture properties are calculated based on the combination of all these different components. These advanced physics provide excellent accuracy and have a very robust implementation, allowing for its successful application in extreme cavitation or erosion conditions, involving very high density ratios between liquids and gases, and very high gas volume fractions. Simerics MP+ contains templates for specific applications. There are templates for gerotor pumps, external gear pumps, and crescent pumps. Just to name a few examples. These templates guide users through the creation and control of a moving mesh, which are the first key steps in creating a successful simulation. They also guide the user through setting up the working conditions of the simulation, as well as the desired outputs for each specific application. This helps the user quickly and easily set up the simulation and get results quickly. The templates cover more than 90% of the PD pumps used today. Low-pressure pump templates include generator pumps, both fixed and orbiting, external gear pumps, crescent internal gear pumps, balanced and variable displacement vane pumps, and also progressive cavity pumps. High-pressure pump templates include swashplate piston pumps, bent axis piston pumps, radial piston pumps, and reciprocating piston pumps. Simerics MP Plus can be used for many different PD pump design and analysis purposes. For performance prediction, flow rate, power, and torque can be predicted at all operating conditions. Cavitation prediction for PD pumps can be used to analyze the volumetric efficiency reduction due to cavitation, as well as cavitation erosion. Transient loads and pressure ripple can also be simulated and used in analysis of vibration and noise. Even leakage can be predicted through gaps. It can also be used for analysis of pump priming, conjugate heat transfer inside the pump, and for different types of fluids, including non-Newtonian fluids. All of these results together help to create a highly detailed and complete understanding of the performance of a certain design. These are very helpful in making informed design improvements. Additional design of experiments, or DOE, and optimization can also be performed using partner products for further design improvement. This slide shows some performance prediction examples. The image on the left shows the volumetric efficiency of a crescent pump predicted by Simerics MP+, compared with experimental data. The center image shows a dual-gear pump design running with a shifted phase in order to reduce flow ripple. Simulation results demonstrated improvement in flow ripple reduction at different phase offsets. Lastly, on the right, we have a variable displacement vane pump with automatic eccentricity adjustment based on fluid force. Again, despite this added complexity, Simerics MP Plus predictions matched extremely well with test results. In terms of cavitation, Simerics MP Plus can perform two kinds of analyses. First, predicting the volumetric efficiency. For an ideal pump, the flow rate grows linearly with the pump rotation speed, as seen from the dashed line in the left diagram. However, in real-world designs, after a certain rotation speed, the liquid supply cannot match the pump speed, and the flow rate will flatten out as seen in the blue line. Simerics MP Plus simulation results, shown as the red dots, accurately captured this. The other important cavitation-based analysis is that of cavitation erosion. In the right-hand image, we see the formation of bubbles caused by heavy cavitation near the valve plate. These bubbles can cause massive structural damage over time as they collapse. This phenomenon was fully captured in Simerics MP Plus and proven accurate when compared to hardware testing. Simerics MP Plus can predict transient loads, pressure ripple, and water hammer phenomena. These results can be used to further analyze vibration and noise in PD pumps. Here on the left are pressure ripple results from a swash plate piston pump simulation compared to experiment data on the right, demonstrating excellent agreement. The pressure ripple can also be output in a frequency domain, with which one can visualize the frequency characteristics of the pressure ripple simulation results and better compare them with experimental results. I will conclude this webinar by going over a few customer cases that demonstrate the advantages of Simerics MP+ in PD pump simulation. These are swash plate piston pumps, where self-priming and cavity erosion have been predicted using a transient dynamic simulation approach. These cases were published at the Fluid Power Innovation and Research Conference. This slide shows cavitation erosion prediction for the same piston pump. In the animation, we can clearly see the regions where bubbles form and collapse periodically near the valve plate due to cavitation. This constant formation and collapse of bubbles can occur thousands if not millions of times over the life cycle of a product and will cause significant erosion on metal surfaces especially. The image at the top right, taken after an experiment, confirmed this prediction by showing significant pitting and erosion at the same locations on the valve plate. Now let's look at a self-priming analysis in which a pump speed is increased until the flow rate curve starts to flatten due to cavitation. The brown red line denotes the Simerics MP+ results, while the smaller red line denotes the results from another CFD tool. Simerics MP+ prediction had an error of 2%, while the other CFD tool generated an error of 16%. Not only did Simerics MP+ yield better results, it also outperformed the competition in every other metric. This comparison was performed by a customer who was looking for a more efficient and more accurate simulation tool to keep up with their design processes. Comparisons of simulation accuracy across 5 different cases were recorded on the left chart, while comparisons of simulation setup time, mesh time, run time, and post-processing time were recorded on the right. This level of dominance by Simerics MP+ in competitive benchmarks is typical. If you are interested in experiencing this for yourself, send an email to the contact information on the following slide to schedule an introductory demo. Thank you for your attention. Please send us your queries to contact@simerics.com.